right. So, good evening, everybody.
Good evening.
Very good. Let's try that. Good evening, everybody.
Good evening.
All right, fantastic. So, welcome to, this is our last normal TWed of the spring 2017 term. Next week is lightning talks. You got to get like a special credit or something. Yeah, it's like I have to do it again. So tonight we're all here to hear Matt Klawonn talk about generative adversarial networks.
Yes.
and actually some of us have been having a conversation. Where did they go? Where did this not go? Alex, these guys. We were just talking about this. We had to open up the door for them. So Matt's going to talk about various different applications of them and how they work and all that cool stuff. And it's very exciting. We just actually found another project tie-in. Professor Bennett and I. There's an interesting way that they could be used for scoring machine learning competitions and stuff like that. So
cool.
So we're really interested in hearing about that. So anyways, just a couple logistical things. This is being streamed and recorded as usual. Just keep that in mind as you fling insults at Matt. Again, please, if you have not signed up for lightning talks for next week, please do. Just check your email, because I send a near daily email to you, reminding you, and I will henceforth until next week. Without further ado, hit it, Matt. Thank you.
Thank you. So thanks everybody for coming. Today I'm going to be talking about, as John said, generative adversarial networks, which have been described by Yann LeCun as one of the most interesting advancements in machine learning in the past 10 years. So jumping right in, we'll first cover a little bit of background so that we can sort of all be on the same page with terminology and that sort of thing. First thing I'd like to talk about is generative models in general. So this is a class of machine learning models that attempts to learn a probability distribution, and in contrast to discriminative models, which try to learn a conditional probability distribution, i.e. given some input, what is the likeliest output for this given input. So commonly, these sort of discriminative models are applied to classification tasks. Rather than being given some input and trying to predict the output, what we want to do is learn the joint probability of the input data and labels simultaneously. So this means that we have not only the capability to generate a label for a given input, but we have the ability to generate the inputs themselves, essentially. Data which comes from the distribution of the input samples that we're looking at. So this is just sort of an illustration of what we're trying to model with the two different approaches. On the left, we have a discriminative model, which is simply trying to draw a line dividing the blue and the red classes. Whereas a generative model, we're trying to learn the entire space that these blue and red classes might belong to. So we're learning, all of this blue, which is not corresponding to a specific data point. What we're essentially saying is, okay, I've learned that whatever class this may be can be these data points themselves, but can also have inputs in this entire, elliptic space. And I'll get into the reason why we might want to learn this entire probability distribution, as opposed to just being able to discriminate between two different classes or between some number of different classes. So one of the advantages that generative models have are the ability to describe the underlying structure of the input data. So going back to that previous diagram, rather than just saying this is a cat or this is a dog, I have some concept about the space in which cats exist or the space in which dogs exist. And I can do this even potentially when there are no labels. So I don't necessarily need to know that two things are separate, distinct classes if I can just sort of learn this probability space over the input data that I'm given. And another really nice thing about it is that I can now generate that data which exists within that probability distribution. So I could, if I'm trying to classify images of cats and dogs, if I use a generative model, then suddenly I have the ability to produce new images of cats and new images of dogs, which is really cool for a number of reasons. So one example of a generative model is a Markovian process. Here we have a comic strip called Garkov, which is essentially Garfield mashed up with a model which has been trained on input text from Garfield. So these captions don't make any sense, but they're still kind of funny, and just shows the sort of things that we can generate using a generative model. So what you'll see frequently in current or in generative models prior to GANs is, it'll pick just very frequent phrases or comic like progressions that it's seen in its training data and put those spit those out as output. So Richard Feynman has a really good quote that kind of summarizes why we might be interested in why generative models are interesting, and it sort of makes sense to our experiences as humans. What I cannot create, I do not understand, he says. So this is sort of going to an course kind of lines up with this idea that if I can generate something, if I can create text for a Garfield comic, or if I can create an image of a cat that I haven't seen before, then it sort of indicates that I have at least some understanding of what a Garfield comic strip is supposed to look like, or a cat is supposed to look like. I've learned an internal representation of these concepts that is meaningful and useful enough that I can generate a new something new that I haven't seen before, but which is still kind of similar. Yeah, question?
So the Garkov model, it was only trained on the text?
Correct, only on the text. Yeah.
So how was the image decided?
It's just random. Somebody just took previous strips that had been drawn and then filled in the text bubbles with whatever the model was outputting. Yeah. Yeah, so that's not correlated in this case, yeah. So there have been a number of shortcomings, though, with generative models, especially in the past. For some reasons, discriminative algorithms generally perform better when you're trying to do like a classification task, probably because you're training specifically on labeled data, which is indicating how to classify various inputs. And obviously, classification is a major, machine learning task that is applicable to a number of domains. So a lot of focus has also been placed on using these discriminative models to do classification, as opposed to furthering generative models for classification, just because we think discriminative models work better, at least up until now, and they give better results. It's difficult to learn a distribution for a given set of that you think a given set of inputs belongs to, and there's some reasons which I've cited here, but one of the primary issues that I'll cover is that if you're trying to learn this via some like maximum likelihood estimation or via various losses, there have been theoretical results showing that if your data lies on a low dimensional manifold within the total high dimensional space that it exists in, then even minor issues during the training process can cause your model to completely diverge and not learn anything correctly at all. So if we think about the space of natural images as an example of this, you're likely to see in any given training data set images which are very similar to each other and images which appear on a lower dimensional manifold than the total dimensionality of the image. So if I have a 224 by 224 image, that's what, 400,000 plus pixels that I have, and my images now are in technically a 400,000 dimensional space. But if I look at where those images cluster along, or in that space, they're likely to be actually on a much lower dimensional support. And there's been theory that's shown that when this happens, the training process for like maximum likelihood estimation can give you either zero updates of zero, meaning you're not learning anything, or updates of infinity, meaning that your model is totally going to diverge and you're not going to learn anything useful. Question? No.
No.
Okay.
I did have a question in my head, but I didn't raise my hand.
Yeah. So the way that people have overcome this in the past is it turns out if you add noise to your inputs, then you can sort of avoid this problem of either not learning anything or your learning exploding. But the problem with this is that it limits the essentially how good of a model you can learn, right? People have found empirically that it really takes adding a lot of noise to your inputs to be able to overcome this problem. And so generative models for a while have been sort of stuck in this, this cap of, we can generate something that's kind of interesting, but not useful for any like real practical purpose. So yeah, there's no real use for content that has been generated poorly that a human can obviously tell, oh, no, that's not really what we're going for here. So this is sort of where generative adversarial networks come in. We want to know, is it possible to overcome the limitations of these previous generative models, learning something via maximum likelihood estimation by using some architecture to approximate our distribution. So the question specifically that was asked when the people developed generative adversarial networks is, can we do this with deep learning specifically? Can we use neural networks to approximate these distributions? So the reason that you're interested, we would potentially be interested in using a deep architecture is that deep learning has achieved state-of-the-art results in a number of machine learning fields, including image recognition, natural language processing, speech recognition, and more. So just as an overview of the rest of the talk, I'm going to talk a little bit about what GANs are, what generative adversarial networks are, what the adversarial training portion of that means, some implementation like details. It's really more of advice based on some state-of-the-art results that have come out very recently. And then we'll look at some examples which have been some examples of GANs which have generated images, and then talk about how we could also generate sequences. So one of the interesting things was that when I was coming up with this talk, searching for people who have applied GANs to like other tasks besides image generation, those results aren't yet done. Almost exclusively, everything has been done on image generation. So there's a lot of space to sort of play around.
I actually misspoke myself before I characterized the interest that just came up as being, somehow scoring or whatever. It was actually synthesizing data sets with identical statistical characteristics.
Yeah.
An example being say a medical data set, like a clinical records data set, where obviously you're concerned about anonymity, protecting identity.
Sure.
But being able to create a synthetic data set using these principles
Suddenly
has exactly the same statistical characteristics, but it's entirely synthetic.
Yeah, so that's the purpose of a generative model, is if you've learned the distribution, I don't have to use anything from that original training set anymore. I can generate my own images which are belong to that distribution. So that would be a perfect application for it. If I can generate images of somebody's face, but that person doesn't exist, it's the machine's wild hallucination, then that's great. Yeah, so that's really interesting.
Rock on, man.
Yeah. So we'll introduce briefly what GANs are now that we know what generative models are. So what we're trying to do with GAN is to approximate some probability. So the reason that I use the word approximate is that neural networks are deterministic models. So these neural networks which comprise the backbone of deep learning don't learn probabilities. They are deterministic. They have some weights. You put an input through and you get the same output every time, right? So in order to use a neural network in a generative framework, this original paper, which came out in 2014, which is proposing GANs, proposes to train the network based on some random variable z. So this z variable is where we are approximating some distribution. And then what we're learning is the probability of some function of z, where this f corresponds to the neural network that we're learning, and our y, our output label. So this f is really where the learning comes in. And you might ask, well, how do we train this? Because let's say we have this f, which takes as input some random variable z and produces an output. I don't know how to evaluate that, right? Evaluating generative models can be difficult. So if I were to say, this is what my model is generating currently, how can I improve? It's kind of hard to say, right? You could say, well, we can say it in loose human concepts. Well, it looks like a little fuzzy, a little pixelated, something's not quite right. But it's hard to put into words, right? Ideally, what you would have is you'd have a human that's looking at each of these labels and saying exactly what I just said, right? Oh no, this isn't good because this is a little fuzzy. Go back and update so that you can produce something that's not quite as fuzzy. And so this is where the adversarial portion of the generative adversarial networks comes in. Essentially, we want this expert to evaluate the generated examples for correctness. And then the goal is to train the generator to produce more realistic outputs, which are trying to fool this expert. And they're based on the feedback of this expert too. So what we can do is we can have, this is sort of the general GAN overview, the GAN setup. We have our generator who is trying to produce something that comes from a distribution. And then we also have plenty of data that actually comes from the distribution that we're trying to model, right? So in this case, it's famous paintings or art or something like that. And as input, this generator just takes some random noise, something sampled from some random distribution. Could be a simple uniform, normal distribution, whatever. And is trying to produce some input so that it can approximate this real data that we're interested in. And our detective in this case is going to be another neural network, another deep learning model. So our deep learning model and our generator are going to play this cat and mouse game where the deep learning critic or detective or discriminator, as it's often called, is trying to pick out which examples have been generated by this forger, this generator, and the generator is constantly trying to update to fool it. And so I'll get into that adversarial training a little bit now. So that, like I said, that generator produces some output. This output is then intermingled with an equal amount of real data from the distribution or from our our training set. So if I have a large collection of images, what I'm going to do is I'm going to have my generator generate a batch of images, and then I'm going to mix that with an equal sized batch of images from my training data. And essentially I assign some label to all of the data which has been forged and all the data which has been drawn from the ground truth distribution. So commonly you say, all right, all my ground truth images are ones, all my forged data are zeros. Discriminator, which do you think are forged or from the real data set? And so this is that specific algorithm just written out in code from the original paper. So you sample some mini batch of noise, and then you sample that similar sized mini batch of, sorry, not similar sized, exactly the same size, mini batch of examples from the ground truth, and also generate that same amount of data using your generator based on the noise that you're giving it. And then you essentially update the discriminator based on what it got right and what it got wrong. So if it's severely misclassifying all of the data and saying like, oh, everything looks real to me, then you're going to say no, half of these were wrong. Please update your parameters accordingly, right? So this is done through your training method of choice. With neural networks and with GANs, we're talking about back propagation. So then once you've trained your discriminator, you also want to train your generator to get better, right? You want to train your generator so that it's producing more and more realistic examples and trying to fool the generator. Yeah, question?
What you just said, if the discriminator classifies all the artificially generated images as real, then in theory, if that was the first iteration, the algorithm would terminate and you would just be done, right? Because you fooled it perfectly, right?
No. So actually, what you're interested in is getting your discriminator and your generator to be as good as they can possibly be. So ideally, what you're searching for is some kind of like Nash equilibrium, right, where neither player in this adversarial game can get any better. They can't select a better strategy. In this case, that we're obviously not there, because what the discriminator could have done was classify all of the generated examples as being fake, right? So just because my generator has fooled my discriminator doesn't mean that my generator is where I want it to be. It could just be that my discriminator is really dumb right now, and I need to make it smarter. So using this specific algorithm, what was done, and I say was because this has actually been tweaked a little bit within the past couple of months. What was typically done was you would train your discriminator a little bit more than you train your generator, because the discriminator is really what's driving training, right? It's no fun to fool a discriminator which has no idea what it's looking at. It's much better to fool a discriminator which has a very good idea of what it's looking at, because if you can get to that point, you're starting to generate really realistic examples. So then once that discriminator has been trained, either for a single iteration or for a couple more iterations than my generator, then I need to update my generator and essentially say to the generator, okay, these were the examples which fooled the discriminator. These were the examples which did not. Update your parameters accordingly. Yeah.
Oh, does the choice of the distribution for Z have a meaningful effect on the output, or does it tend to not matter that much?
It can. So what we'll see in a little bit is that you can select these inputs to this network that are not drawn from like a simple distribution like a normal or random. They can instead be drawn from training data. So if I'm trying to predict if I'm trying to generate a sequence of images that form like some moving picture, then what I can do is I can take I can condition my generator based off of the first image in that sequence and have it predict the future essentially. So this was a project that was done in June or July of last year, where they take essentially an encoded picture, some which has been reduced to some like fixed dimension via a convolutional neural network, and then they feed that as input to the generator, and it learns to generate somewhat realistic progressions of that image through time. And so you can think of that as drawing from this probability distribution of the images that it's being trained on, as opposed to just like totally random noise. So yes, it does affect it. The difference between two simple distributions, though, is not likely to be huge. So if you were to use like a random uniform versus a Gaussian or something like that, it probably wouldn't be too crazy. Good question, though. Yeah, so in terms of what we're actually doing to update each of these networks, I'm essentially training the discriminator based on some binary classification, at least in this older method, and then using like a cross entropy loss. So I'm trying to get it really close to saying 1 when the thing is from the real distribution, and really close to saying 0 when it's from the generated distribution. So diving into how you sort of implement this in practice, this is sort of a cop-out. I wrote some code here, but it's all comments. So basically, I write my generator in whatever framework I'm interested in. TensorFlow, Keras, there's lots of deep learning frameworks out there. Probably most of the people in this room are familiar with at least one. So this is something which accepts, a vector of inputs, which could be random noise, could be, an encoded image, could be, anything that's coming from some distribution. And then I'm going to take its output. I'm going to generate, a mini batch of outputs from this generator. and I'm going to mingle that with a data batch which has been sampled from my ground truth, my training data set that I have access to. And then I'm going to train the discriminator based on these combined inputs, update the discriminator for whatever number of iterations, and then update the generator with error that is propagated back from the discriminator. So for the things that the discriminator got right, essentially that's bad for the generator and it wants to go the opposite way. So yeah, it's pretty, honestly, these things, there's a lot of theory or a lot of math and diagrams of algorithms behind them, but in practice, using like these deep learning frameworks, they're not terribly difficult to generate. So there are some problems though with this original GAN formulation that it's sort of limited them from realizing the true potential, maybe. So GANs have kind of come onto the scene since they've been on the scene since 2014, and they've been able to do some interesting things, but haven't like taken over deep learning or made a significant dent in other deep learning. And the reason that one of the reasons that this might be true is because there are some serious problems with training these original GANs to produce anything actually interesting, and there was a lot of guesswork until very recently. So one of the reasons is that this loss function that we have, if I'm examining the loss of the discriminator and the loss of the generator at any given time, it's kind of meaningless. And I say that because a discriminator, like that question that we had earlier, the discriminator could be getting perfect accuracy and have zero loss, but maybe that's just because our generator is terrible. Or a lot of the times you'd see the losses start to kind of diverge together, so get really high, and now I lose interpretability, and the training process becomes a little bit unstable. And so I just covered all this. And this paper, which introduced what are called Wasserstein GANs, or WGANs, essentially argued that the problem was that we were using the wrong loss function. So we were simply trying to use a cross entropy with this sigmoidal output of the discriminator to train the discriminator and then the generator. And the problem was that they actually showed that this is equivalent to trying to maximize the Janins-Shenson entropy. I don't know if people are familiar with that, but basically, if we go back to that original problem that we were having with generative models of data appearing on a lower dimensional manifold, then even small instabilities where we have the distributions of the generator and the discriminator being separated can lead to real training instability. So our gradients can become massive or can be zero, and we're not ever going to learn anything. So what they did instead was they just replaced this loss with another metric called the Wasserstein distance, also known as the Earth mover's distance. And without getting into the nitty-gritty details, Wasserstein is essentially supposed to represent how much work it takes to move some data from one probability distribution to the other probability distribution, which is why it's called the Earth mover's distance. You can picture it as if your two probability distributions are like mounds of dirt, and I'm trying to get this one mound of dirt over to where this other mound of dirt is, then the Earth mover's distance calculates like how much work I have to do to move all of that data over. And so they show that this has much better performance in practice. You don't deal with those instability issues. The loss becomes a little bit more interpretable. So if my generator and my discriminator both start getting really small losses, then that means I'm probably approaching that equilibrium that I'm looking for. So there's all these nice properties, and it's probably I would say it's the current recommendation of generative adversarial networks to use.
The Earth mover's distance, is that just the sum of the differences between the sum of the deltas? Or, I mean, if it's two distributions,
Sort of.
You don't have I guess it's the area under the curve, so it's the sum.
Yeah, it's
The integrals or something.
yeah, yeah. So we'll look at an example of how to calculate, or of where the Earth mover's distance, it becomes much better than using these previous metrics. So I've just talked about this, and this is the image that I was talking about. If our real data is random uniform between 0 and 1 on some value 0, and our fake data is currently at 1, they show that all of these other metrics for measuring actually show that you should be updating by 0, which is obviously not what we want. We're never going to learn anything. We're never going to get our fake data to approximate our real data. But with the Earth mover's distance, it's just the difference between the two. It suggests you move 1 over, essentially. So it's nice and a simple example to show why it's better. So yeah, use Wasserstein GANs if you're going to get into generative adversarial network training. So in terms of how complex these things are, how difficult they are to train, it's about as difficult to train as other deep networks. So, you know, because you have a generator and a discriminator, maybe you have, you know, more parameters than you would in just training a discriminator. But one of the biggest things is that you're essentially doubling your data set size, right? Because you have some training data input that you're sampling from, but then you also have your generator, which is producing data that you're going to feed into your discriminator. So one consideration to make is, because you're generating this data as you go along, you might want to consider trying to speed up this phase by like queuing. So while your discriminator is doing its updates based on the batch that it just saw, you might want to be creating new batches so that you can have them ready to go for the next time around. Yeah.
So the Earth mover's distance is involved in updating both the generative and the discriminative models, or only the discriminative?
Both.
Okay.
Yeah, so whenever we're training our generator and our discriminator, the generator's training is going to be based off of which examples fooled the discriminator and which examples didn't fool them. And so inherently you have to use the discriminator in order to update your generator, and the discriminator uses this Wasserstein loss. So that means that the generator is, you know, using it too.
Did you show the formula for the Earth mover resistance somewhere?
I did not, I don't think. So it's the product over all joint distributions, or all joint variables for each of the distributions. So I can bring it up if you like, but it's a little staring at.
I can look it up on my own. I don't want to interrupt.
Yeah, no worries. So it's a little opaque to stare at initially, but there are some like intuitive, nice explanations online for why it is essentially trying to move data from one distribution to another. Yes? Sorry? Yes, they do. Yeah, so there's actually Wasserstein GANs available in TensorFlow, Keras. That's the nature of deep learning. It's like 2 weeks after somebody comes out with a new thing, somebody else has already implemented it and said, no, this doesn't work. We have to do this instead. It's crazy. No, literally the Wasserstein paper, the paper that proposed Wasserstein GANs came at a week after this other paper showing why these previous methods were failing. It was by the same group, but still both of these got put on archive. And then within like 2 weeks, they've got 30 citations. Hasn't been peer reviewed yet. It's just crazy. That's a whole other talk, is why deep learning is out of control. But yeah, so
it's the Wild West.
It really is. Yeah, people just throw stuff up and then everybody else uses it without like, hey, wondering, is this like going to break something catastrophically? Or yeah.
So you need like an RSS feed on archive and just every morning.
Seriously, yeah.
Or you just need to train a neural network to discern between good papers and bad papers.
Or maybe a
generative model to
maybe
generate
to
good
write
papers.
Maybe they're already doing it. Maybe that's
There
why it's
probably
so
are. Yeah, who knows?
That's right. Yeah. Is this the real paper or is this my
Yeah.
Or
Yes.
you're the function D.
Talk about this. And when you're going to use your trained models, you simply, so for example, in TensorFlow, you would simply call that generate op once your model has been trained. to get that generated data. And there are lots of uses for the discriminator too. So we've sort of, with this adversarial setup, we sort of end up with something that can approximate, this joint distribution of labels and, the data itself. So if I can generate like lots of images of cats, lots of images of dogs, whatever you want with the generator. But I can also use the discriminator to, for like classification type tasks. If I take this, network which has been trained to differentiate between fake cats and real cats, it probably has a pretty good idea of what a cat looks like at that point. So if I want to use it for classification, I would just say, okay, here's a bunch of images of cats and not cats. Use what you know already to train and update based on this specific new data set that I'm giving you. So it's been shown that these discriminators actually can use like fewer parameters to approximate, or fewer parameters for like classification tasks and get really good accuracies. One thing that they've tested this on is the MNIST data set. So a model which was trained to discriminate between real MNIST data and MNIST data that was generated. If you get extract the features, sort of that last hidden unit within that network, that discriminator network, and use that as input to a simple like multi-layer perceptron or like even a linear classifier, you can get like upwards of 99% accuracy just because this internal representation that it's in is really good. So it's using this approach gives you all sorts of nice benefits.
So you wonder, applying it to MNIST, if you're using it to generate, does it come out with? I'm like trying to envision what you see, because MNIST sort of looks like this handwritten set of characters.
I'll show you what it looks like. Yeah.
Cool.
So if we're trying to generate some images, what we need is obviously a collection of images, some ground truth data to sample from, generator, your discriminator, and typically what your generator is going to do is it's going to use what's called a deconvolution, which is essentially a convolution in reverse. So if you're interested, you can look at this this formula, which is from the deep learning class that I'm taking right now, actually. But basically, with a convolution, we're sampling from an input volume, and we're using some filters to extract features from this input volume. And with a deconvolution, we're just literally going the other direction. We're going from a smaller input volume collection of like some features, and we're producing an output. So you do this multiple times, and you end up with something that looks like an image. So this one in particular was probably the first one that used convolutional nets to generate MNIST, artificial MNIST data, artificial handwritten digits. It's called deep convolutional GAN, appropriately. So it takes, as we talked about before, it takes that random noise, that 100-dimensional Z vector as an input, and then slowly uses more and more deconvolutions to produce what's essentially a 64 by 64 by 3 image. Yes?
Is the fact that you're doing deconvolution the reason why you need that random noise?
Yeah, it has to pull.
Inverse, so you're going to get zeros in the denominator.
Yeah.
You're trying to avoid that. Is that it?
No, it's not real convolution. This is
Well, I mean, I'm talking about deconvolution.
yeah. Well, this
It's
is why.
inverse convolution, right?
Well, it's bullshit convolution.
It's what?
This is their use of convolution in neural networks is it's not what we think of from a mathematical standpoint as
I mean,
convolution,
convolution is convolution.
Sure.
right?
I mean,
because convolution, the reverse convolution is convolution, but
yeah,
Convolution.
transpose.
but here they have, because they're using a funky notion of convolution and convolutional neural networks.
I mean, it's
they have
still
to
it's a
come up with
convolution. It's just
Dust off your Z transforms, John. We'll go over it.
No, but this is bullshit convolution. I mean, it's a different notion of convolution that neural networks is adopted.
yes, right.
I'm sure that's why the random noise is.
Sure, and it's I mean, yeah, intuitively it has to pull from somewhere to start generating bigger input volumes, right? So this random noise is this, this variable that we're, this distribution that we're applying a function to, and then we're learning to approximate we're learning the joint distribution of these, this function of this random noise and this data. But if you change this to, like I was mentioning before, 100-dimensional vector, which is some representation of an image, then suddenly maybe I can start producing, like videos, video prediction, where I have, a series of images that's based off of that initial frame that I got.
But this is reproducible, right? So that
If you have the seed,
so that's
it's
a seed,
deterministic.
right? And so it's repeatable. So
Yeah.
you repeat that seed, you're always going to get exactly the same result.
Correct. Yeah. This deconvolution process is deterministic. Yep. Oh, bummer. Didn't embed. All right. We'll go to the video itself then, if I can get it up.
Let's go to the video.
Yeah. There we go. So let me just find this.
Has this been tried with vector spaces instead of images?
Trying to generate something from a vector space?
Yeah, like trying to generate the vector profile for a particular condition. So you have a set of attributes on
Well,
something.
you can sort of think of an image as
Well, yeah,
it's just
yeah.
a collection of however many pixels that you're trying to approximate. So it's just the same task. I don't know what other output you're trying to approximate though.
Well, I'm trying to approximate so if I have a set of examples of a particular, so like a genetic profiles of a disease state, and I try to adversarially generate examples.
So is that a
disease.
continuous vector? Or is that a discrete vector?
It's usually, well, it's a continuous vector across thousands of dimensions.
Sure. So I'm sure you could adapt the framework to do it.
You could go forward.
Yeah, that's like
Yeah.
what John's talking about.
So for example, we have, this is not MNIST, this is not what I was looking for exactly, but this is a network which is being trained to generate like Pokemon sprites.
I don't know. I still see it.
Yeah, I'm plugged in. I just don't the projector. Yeah.
Oh.
So
Coming in now.
yeah, you can see it. It like starts off with pretty random shapes, and then starts to kind of, approximate things which look more and more like Pokemon, but not quite there. So
It's like they're trying to materialize.
So
yeah, they're
can
trying.
you give a what? So we see this grid. What are the different things?
Yeah.
The different things in the grid are essentially just like different random vector inputs. So if you have the same set of random vector inputs, then you're going to get the same set of images for each version of the trained network. But what we're actually watching is the training process itself happening. So we're seeing this, this test data set that's being approximated, and then the network is learning how to update to try to make it more and more each input. Each function of the function over each input more and more like a Pokemon, right? So in summation, it's trying to learn, what like a good representation for a Pokemon is based on some random input.
Do you have to? So you have basically lots and lots of examples of Pokemon of different kinds, and it's able to basically generate those examples across many different ones, or do you have so?
So at each training step, right, the discriminator is going to get a batch of real Pokemon and a batch of generated Pokemon, and it's going to all it's trying to decide is whether or not that was a generated Pokemon or a real one. Yeah, there we go. That's what I want. We'll start from the beginning too, so we can kind of see. And we can speed this up maybe. Yeah. Because we don't want to watch 27 minutes of it trying to learn how to draw a 7. So yeah, again, starting out, this is just, it kind of looks like random noise, right? Because that's the vector that it's getting, and your network is probably initialized randomly to produce these outputs. But then as the generator trains, you start to see it really differentiate between numbers, be able to generate different numbers, and then also to generate more realistic numbers. So if you'll recall in the beginning, and even now, a lot of these squares are sort of like evolving together. But as we go along, we'll see that it starts to specialize depending on the noise, and can create, a realistic looking 7 for one given input and a realistic looking 8 for another. And the results that you get are actually pretty good. So this would be a good time to.
So it's like, I can make a 1.
Yeah.
Okay.
Right. So yeah, this would be a good time to take some questions while we watch this learn, if people have any so far. Yes.
So when you have your optimal generator, is that going to be, is the only way to look at the distribution that it generates by sampling from it, or is it going to be parametric in the sense that you can try to characterize its distribution in terms of the parameters that it's learning?
I don't think it's quite so simple as
So
being parametric. I think you have to run some some noise through the generator in order to generate the actual sample. You can't say ahead of time necessarily what inputs are going to be generated given some property of the noise. So that's a function of neural nets being kind of hard to read into, and black boxes, even though there was a talk last week which kind of suggested they weren't, which I have my own problems with. Yeah. No, yeah, keep going if you.
Does it do any kind of feature selection that you're aware of?
Yeah, the discriminator does definitely, because it's got it's been shown that these these features that it learns internally are very powerful enough that even a simple multi-layer perceptron or something like that can get really good accuracy on a classification task. So that's sort of the whole point of deep learning, is that it's optimizing its feature selection based on the task at hand. So you would expect, if your generator is generating really good samples, then you would expect that the features internally are pretty good and representative of the data that you're getting. That's probably more true for this adversarial approach than it is for another deep learning approach.
Yeah, so I'm wondering if it would be kind of pushing the discriminator towards these features.
Yeah, yeah. So this is actually one of the motivations of adversarial training, is that in the past, deep models and plenty of other machine learning models for that matter have been really easy to fool, in the sense that you can take an image, add some random white noise to it that changes it imperceptibly from a human's perspective, and so suddenly it totally changes the classification of that image. So there's a common one where it's like a panda, and it goes from being a panda to being a gibbon with 99% accuracy, or with 99% confidence, excuse me. Sorry, it's been carefully selected so that it can fool the classifier. Yeah.
Is the discriminator operating over the entire set, or
one batch at a time?
Okay.
So this output is for a fixed set of noise vectors, which is why once you.
Oh, so this is the same as with the images that we saw, where each one was a noise vector.
Correct. Yeah. So what's kind of cool is you'll see this noise vector, like this one in particular, is changing a lot. So you'll see that this fixed noise, it's kind of flip-flopping. It's trying to decide, is this more like a 7? Is this random noise more like a 9? Can I make a better 9 out of this, given the parameters that I'm learning based on the updates of all these other examples too. But yeah, once it kind of, for a lot of them, it'll kind of settle in on 1, and then like this 0 here, all it's really doing is kind of changing little squiggles, making it a little wobbly. Eventually it might flip to another number, but right now it seems like it's pretty stable. Like that Z vector was set for 0 for a while. That's over thousands of epochs though, so as it's updating over time, you would expect maybe it'll change, but it's kind of
This picture could kind of be analogous to like a validation set, right? You're training
Yeah.
on different randomly generated noise at each
Yep.
iteration of
But the validation set is sort of
this
held.
phase.
Yeah.
Okay.
Yep.
So does it reach, because what it seems to be doing is this is sort of anthropomorphizing, but it seems to be settling where it's toggling between one thing that looks like what we recognize as a number and another thing, or so it's
Yeah,
kind of
so-
going between states that are each end state is recognizable, but then it's
Yeah. So that's kind of this was trained using that previous GAN method. So this is something you'd see a lot, especially with that. I don't think it's necessarily as true with the newer Wasserstein GAN. But this idea that you want to converge to a Nash equilibrium is nice, but it's not what happens in practice. Usually, so what's happening here is there's a cat and mouse game where the discriminator starts to remember, the generator's tendencies, and even though they might look realistic, you're still training everything, right? So the discriminator at each point is really still trying to catch on to what the generator's doing, and even if the generator's doing something realistic, then it might say, "Oh no, you have a bias to create 7s or something like that instead of creating 3s," or all your 7s have this little notch on the end of it. Even if that's something that appears in the training data, then it can catch on, and so the generator has to change and produce other different realistic images.
That's interesting because the MNIST does have those. It has those
Sure.
little irregularities.
Sure.
So it's kind of learning those irregularities.
Yeah. So the tagline for this new GAN, this Wasserstein GAN, is that it trains a critic instead of a forgery expert. Right? So if you're producing art, it's not going to say "Oh no, I think that's forged." It's going to say, yeah, that's interesting subject matter. Good job." So at least that's a quote straight from the author of the paper, who's trying to explain it. So yeah, you don't get so much of this cat and mouse kind of game where the generator has to change even though it's doing a pretty good job. But you had a question? Yeah.
For example, this experiment is to detect the artificial examples from those MNIST. What examples that actually look like natural digits? Yeah.
MNIST, you're saying that MNIST doesn't look like handwritten digits?
No. You say that the goal is to detect the generated examples from those which actually exist in the X.
Correct.
What about the generated examples that are actually looking like 0 or 7?
Right. Yeah. So then you're probably getting to a point where your discriminator is going to have a really hard time differentiating between a real and a real sample and a generated sample. And so then, depending on what your loss function is and depending on which GAN you're using, you can end up with probably what we're witnessing right now. That looks like a lot like an 8, but the generator is sort of being forced to change because the discriminator is trying to catch on to every last little detail that it can get its hand on. Even if it looks realistic, there's always going to be some little signature in there that it was generated by the generator as opposed to a human. Even if it's the discriminator just remembering how the generator writes. So yeah, the discriminator and generator are getting to know each other really well as training goes on.
How many examples does this need generally?
So that's kind of the interesting thing, is that you're generating your own examples as you go along, right?
Yeah.
So if you have it, typically the tagline is that deep learning requires massive amounts of data. But in these cases, they find that you can sort of get away with a little bit less than what you might have needed previously because you're essentially doubling it. Whether that means you can go from 50,000 MNIST images to 25,000 suddenly, I don't know, but maybe you can get away with 40 instead of 50 or something like that. So I don't think there's a hard and fast rule, but you probably won't need any more data than you would need for another deep learning task. Yes.
Does the dimension of the random noise to start with, is this because before the deconvolution begins, Yeah, what was the dimension of that random noise?
It's just 100.
How the dimension?
Yeah.
Like, so like what, 10 by 10?
It's just a row vector.
It's a row vector.
Yeah. So just 100 values in a row vector. Yeah, so you could imagine that having some kind of effect. The difference between like 100 and 101 is not going to be perceptible. But if you're using like a single random value as opposed to 100, then it doesn't have as much information to draw from in order to generate a new example. And so the diversity of the outputs that you're going to get is not going to be as high intuitively.
Like versus overfitting in terms of like the variance of the output, maybe?
Less, you would have less variance in the output. Yeah.
So one of the points you made earlier was that as part of this process, you're developing a really good discriminator.
Yes.
Right? Okay. Which in itself is a useful thing, and that's kind of your point. You're just making, you're generating your own examples.
Yep.
At what point in this process did this, as we've been watching, the total video was like 20 some minutes, right?
Yeah.
At what point did it become a really, really good example of evidence?
It's kind of hard to say, right? So if you start fooling your discriminator and you think your discriminator is good, then that sort of indicates that the point you've gotten to is good. Your generator is at a good point. And so that's kind of why it's nice to have an interpretable loss function, because if suddenly my discriminator loss is like really low, meaning it does a good job classifying between the two, that means I have a good discriminator. And then if I see that my generator starts to catch up to it and the discriminator loss goes up a little bit, it probably means that if I trust my loss function, it probably means that now my generator is also really good, because my discriminator was good at some point. My generator caught up to it and made it stumble a little bit. But
when it became a forger.
Yeah, but in the end, it's going to be, it has to pass the eye test, right? So what the goal is to produce something that a human also thinks is reasonable, and sort of at what point you can stop and say, yeah, that's good enough. It hasn't been set yet, so this is a new enough field that we have some idea. You train it for 50,000 iterations.
So where are you going with this? Is this just background, or is this?
So this is GANs, what they're about, examples of GANs, and then I'll talk about one of the. There's the. That one worked. The other one didn't. People have, so I'm going to talk more about what people have used it for, and then what I think I could use it for in the 0 minutes that I have left.
Yeah, the 0.
Yeah. So this is an example that's frequently cited. They use GANs to produce super resolution versions of images, which are just as sharp, if not sharper, than the original.
Sort of like cop shows.
What's that?
Zoom in.
When they zoom in.
Yeah.
Can you clarify that image?
Enhance.
Zoom into nothing.
Exactly. Yeah.
It's getting something from nothing. That's awesome.
Yeah. And we can see previous approaches, things were a little bit blurry, but and this one was generated with a really deep network that wasn't trained using an adversarial approach, but you get this really nice sharpness when you use GANs, and that's one of the things that's sort of taking the image processing world by storm, is that they can generate these super sharp, pretty realistic looking images using this approach. So you can, like I said, there's a multitude of uses for the generator. If you want to generate data, for example, use medical images that are now anonymized because the person doesn't exist.
Actually, I was referring to not so much imagery, but just data.
Sure.
Just clinical
Yeah.
data, whatever, and just synthesizing stuff that's statistically identical.
Yeah. Yeah, so it's tougher to generate discrete stuff than it is to generate continuous stuff.
But this would be,
But
yeah.
That's why I was thinking the genetics would be interesting, because you can do, it's basically it's a continuous matrix that we can get examples of, and then use that as a classifier and say, hey, is this kind of cancer?
So the challenge, or an example of the challenge, is when you've got certain classes of data, like health data. Right now, it's extremely difficult. It's difficult for us to train data scientists to do health informatics without putting them on the real data.
sure.
Okay, and that data is hidden behind HIPAA, and et cetera. But if you can generate statistically identical data that you can just
Yep.
use in a teaching environment,
Yep.
then they're doing for reals.
Yep.
And similar characteristics. You name industrial data that's locked up right now because of trade secrets, but creating within limits as long as you can't identify the source.
Right. Yeah, there was a tweet by Andrei Karpathy. I don't know how to pronounce his name, but he's a big player in the computer vision field and uses convolutional nets a lot. He said, I'm looking forward to it'll be interesting to see in 30 years when when we'll be talking about good old handcrafted entertainment and not the infinite content that's being generated by machines for personalized to like each of us. So you can imagine, if I can generate images now, maybe in the future I can generate something that like looks like an action movie.
So is this being used now in the generation news?
I don't know.
There are
I'm not going to get
similar,
into
The discriminative functions.
right? Well, there are generative algorithms that are being used to create standard standard like boilerplate type news items,
So
especially press releases.
whatever.
So this is just briefly talking about like that idea of generating a sequence of images from a single starting image. So this is the framework that was used for this particular paper, which I forgot to cite. Shoot, it comes from a group at MIT that generated. They got these horrifying looking GIFs essentially out of these starting images, but they were at least like kind of realistic.
The deep dream stuff.
Not deep dream. So this is a little different. This one, they got like images from a couple of different classes, or moving like GIFs essentially from a couple different classes of scenes. One of which was hospitals, and that was by far the most disturbing one because they had like these pictures of patients and their like faces would like mangle and then like disappear.
Star Trek transporter.
Yeah. But some of them were pretty cool, and they got the natural scenes really well. So like there was images of like rolling waves on a beach, and it's hard to tell even that they've been generated and they're not real. Occasionally you'll see like two horizons, and that kind of gives it away. But
That's all.
Minor details.
yeah. Yeah, no, there have been like two ones where there two suns have been generated. Yeah. So yeah, just to briefly talk, unless you had a question.
No, I was leading into that.
Okay. Just to briefly talk about something that I wanted to try with this. So as I mentioned before, like generating sequences. Sure.
Yeah. So I was wondering if you consider like this could be used like, I don't know, sort of like problematically in like security-wise sort of thing, where like people are just generating fake data off of some sort of distribution that they want other people to see, and then like dispensing that sort of data or like enacting it somewhere, and then so like maybe our tracking.
So like if you're doing a phishing attempt, trying to generate a really realistic looking like notice to send somebody.
Yeah, yes, or something like that.
Yeah.
Or I was also thinking it's like if like say like a terrorist group was using like some communications, right? And in order to cover it, like they generate a random set of like normal looking conversations or whatnot to sort of like.
Yeah, so there's you can sort of think of the like your network design as a key there, right? And if two people have the key, then what I can do is I can take some message like meet me somewhere at such and such a time, run it through my generator, and then suddenly it outputs like a tweet that doesn't look anything like it. But if I have access, if the other person has access to that tweet, can download it and then run it like essentially back through like a decoder, then you could think of this as like something where you can apply or you can disguise message passing, whatever. The problem with like a security environment where you're trying to maybe fool a computer and submit packets that get it to do something that you want is that you're not going to have access to like all the successful packets necessarily that have gotten through, and then be able to like make your thing look like that and also contain all that information that you want it to. I would think that that's pretty tricky. And if you do that for long enough, you're going to get noticed.
Yeah.
So the world isn't falling in terms of like, oh no, this is going to break all of our security measures or anything like that yet. But maybe something to think about. So yeah, sequences and GANs. We've looked at generating images. What if we want to generate a sequence? It's pretty unexplored, largely because recurrent nets are kind of tricky to train in the first place. And you have to produce like a continuous output in order for the GAN setup to work. So what you could do is you can output out like a probability for a collection, like a vocabulary that you want to output if you're doing a natural language processing task. At each time point, I essentially have a probability assigned to each word in my vocabulary that this is the word that I'm trying to predict at this time step. But that runs into its own problems, like very large vocabularies and things like that. But I still think it could be possible. And what I want to do with it is, what I sort of have done with it a little bit, is generate what are called scene graphs based on images. So rather than random input to our generator network, what we're going to input is an image like this, that has like a collection of objects in it, babies, whatever. The bounding boxes for these objects will not be included in the input. And then I essentially want my generator to produce what's called a scene graph, which is just a graph where the nodes are objects in the image and the edges between the nodes are relationships between these objects. So here we can see we have like a triple that is boy is in front of the blinds. And I want to be able to generate these triples and train the discriminator to try to pick out which triples come from the ground truth data set and which triples have been generated by my generator. And then if I can get the generator good enough that it can generate realistic scene graphs, this has all kinds of applications. So there was a paper that showed that using these scene graphs for image retrieval as opposed to like the image itself and just some text underneath it produced much higher precision and recall. And there's a lot of other applications of scene graphs that I can think of, but I'm negative 10 minutes of time left. So yeah, this is how the GANs could be used for this particular task. And then I had some future some reading. So this was the original GANs paper is on top there. It was by Ian Goodfellow, who is now at OpenAI. And then these Washington GANs were recently introduced by this the TW's group. I forget where they're from specifically, but they do a lot of good theoretical work.
I added a couple papers to the
yeah, and there's papers in the emails and links to tutorials and stuff. Yes.
So using these scene graphs, can you envision a way of say tracking an individual on security?
Sure. Yeah, through a city even. So if you have like lots of security cameras and you know what a person is wearing, then suddenly I can just I can look through that large collection of images, generate scene graphs for each of them, and look for ones in which there's only a man who is wearing a shirt. The shirt is red and he's wearing a hat and the hat is white or something like that.
So another application that's interesting to me at least is sports analytics.
Yeah.
Tracking players on the field.
Sure.
And ball or puck or whatever.
Yeah, so that's you can definitely apply these to like sequences of images, right? And then it'd be interesting to see what you'd want to do is you'd want to examine how the scene graphs are changing over time, right? So in that first in one frame you might have player is like running or something like that, and then in the next frame player is on the ground.
Well, I think what you want to do is for a vector for each player over a certain period of time, then do analytics on those vectors. And this method is how you generate the vector and travel of that each individual on the field. Yeah. And the ball or the puck.
Yeah, it at least would give you like insight into that person's state at any like given time, if it's accurate.
Interactions.
Yeah. Yep. Exactly.
All right. Let's thank Matt.